if a sphere meets the cone is where r is equal to 2, and we get that just by setting the equations for these surfaces equal to one another. So this is something that often happens is if you're taking the difference between two surfaces that define a solid, top minus bottom, it's possible that those surfaces might intersect. So you need to figure out where they intersect in order to determine your limits of integration. On the other hand, what I could have done was instead had imposed a different limit on r. Maybe set r equal to 1. So then I would only take this cylinder. See where the solid intersects at cylinder, so then r is only between 0 and 1. But I decided, let's let the surfaces meet, and that happens at r equals 2. So that's our limit of integration. And these planes, y equals 0, y equals x, define the limits in terms of theta. So now we have something that we're ready to integrate. So, anytime you have surfaces like this that are defined in terms of x and y that define boundaries of a solid, often those will give you your limits in terms of theta. Whereas if you have functions that depend on x squared plus y squared like we have here and here, those will tend to define your limits in terms of r. Alright. And because this is the top surface, this is one that goes in front, the other one gets, this is the one that's on top. So that's why this one goes first. Compute the volume of this oddly shaped bite of a snow cone. This. Now, alright, I'm going to break this up into two terms. So we're going to have r square root of 8 minus r squared dr minus 0 to r squared dr. We could do these separately because you would use a different approach for each one. How are you going to do that one? Substitution. What's the substitution?
U equals 8 minus r squared.
Yeah, u is 8 minus r squared. So then du is minus 2r dr. So dr is minus du over 2. So now we're going to get an integral of minus 1/2 square root of u du. We don't have to compute the limits in terms of u, but if we did, what we would get is the lower limit is when you plug in r equals 0. So when r is 0, u is equal to 8. When r is 2, u is equal to 4. So we actually have the integral from 8 to 4 square root of u du minus, and we're not doing anything with this one yet. Alright, but here we're integrating from 8 to 4, and we have a minus sign. So we might as well flip the limits and change the sign. So now we have plus 1/2 from 4 to 8, u to the 1/2 du, and then here we have minus r cubed over 3, it's evaluated at 0 and 2. Okay. So now we can finish this off. So now we're going to have 1/2, 2/3 u to the 3/2 that we get from anti-differentiating u to the 1/2, evaluated at 4 and 8. And then this is just going to give us 8/3 d theta. Now, once we plug in the limits, unfortunately, it doesn't work out all that nicely. Well, when we plug in the lower limit of 4, 4 cubed is 64, the square root is 8. So the lower limit does work out nicely, but what we end up getting is 16 square root of 2 minus 8. And then we still have the minus 8/3. And all this is integrated over d theta from 0 to pi over 4. Now this is independent of theta, so all we need to do is take this constant, 16 square root of 2 minus 8 minus 8/3, and multiply it by the difference between the limits, which is pi over 4. And then you, so then you get the final result that way, which is 4 pi over 3 times the square root of 2 minus 1 once you simplify everything. You see here we have all multiples of 4 divided by 4, so that causes a lot of cancellation. And sure enough, the answer, square root of 2 is 1.414 roughly, so we get the positive answer that we would expect. 12.3, number 26 in Stewart. So it's the integral from, so described in terms of x and y. So from 0 to 2, and from 0 to square root of 2x minus x squared, square root of x squared plus y squared, dy dx. So the idea is you convert this integral to polar coordinates and integrate it that way, because expressions of this form
Aren't fun.
what?
They're not fun.
No, they're not fun at all. They require trigonometric substitution, kind of want to avoid that kind of thing. Now, but it's kind of hard to understand from this description what this region actually looks like. So we're going to do a little manipulation to try to get a better idea about that and how it would convert over to polar coordinates. Because we see, if we convert the integrand to polar coordinates, it's just going to become r. So at least that part's going to work out nicely. But what about this region here? Well, to do that, I'm going to do a little trickery here to try to express this into something that's more circle-like, that involves nice, perfect squares. So what I'm going to do is I'm going to add 1 and subtract 1 plus 2x minus x squared. So I'm just taking this square root up top and rewriting it. So now, with it written in this form, what can we do with it to get a nice simplification involving a perfect square? 1, and then the rest of this, if we factor out to minus, we get x squared minus 2x plus 1. But this is x minus 1 squared. So now we can write it this way. All right. So now, but we still need to get an idea as to what it looks like. Well, let's take a simpler function. What does 1 minus x squared, so y is equal to this? What does that function look like? Y is equal to the square root of 1 minus x squared instead of x minus 1 squared. So if I were to graph this, what would it be? It would be the top half of a circle. The unit circle, radius 1. Oh, that's bad. Yeah, so this is y is square root of 1 minus x squared. Circle of radius 1 is just the top half. Well, how will we get this from that? What's the difference between the graph of this and the graph of that? You shift 1 unit to the right, because x is replaced by x minus 1. So we get a top half of a circle shifted. So this is y is equal to 1 minus 1 minus, or x minus 1 squared, which is the same as 2x minus x squared. So now we see what region we're actually integrating over. It's this region, because x is going from 0 to 2.